sorry that when I basically stopped the recording because I need to take breaks between the different recordings, you got this like infinite number of windows. Um, I'm hoping to be able to solve this with OBS, which is the software that I use for recording. Um, and well, I will probably not use this platform anymore. So, why not use processes? As I sort of said, that threads have a shared address space. So if you're basically operating on the same data structure, for example, it sometimes makes perfect sense to use threads rather than processes because, well, it is the same data structure. So it doesn't make sense to basically start a process for taking just one element in that data structure to do computations on. So threads are a natural choice when constructing programs where you need shared data structure, but you want also to have some form of parallelism in the system. Processes are better when you have more distinct separate tasks where little communication and sharing of data structures is needed, where less sharing of data structures is needed, basically. But life is more complicated than that. And this is actually from outside three easy pieces. Operating systems and operating systems design operating system designers, because the operating systems are not to blame, they have done way more systems than can be presented in a single course. Basically, they have implemented and built way more systems than I can basically cover. But threading models is one of these complicated, very fanatic things between operating system designers. There are multiple models for threading. One of them is called one-to-one kernel level threading. One of them is called N-to-1 user level threading. One of them is called M-to-N hybrid threading, and one is a hybrid implementation from all of these. You can read a bit more about this on Wikipedia. There is the Dinosaurs book. There's an operating system book that people call the Dinosaurs book. I do not know how to say the name of the author, but it's Cibernacci, I think, or Cibernacci. Can't remember. That basically discusses these models in much more details. And the whole idea is that you have at the kernel side an implementation that will basically that covers for the threads. I mean, you have a thread that is running on the user level, so you have a program that is multi-threaded, and then you need to do something at the operating system side, which is what we care for mostly in this course, to actually implement these threads, to make these threads work. We are going to cover a little bit of this over the next couple of slides. So the PCB versus the TCB is actually not as simple as I introduced that. It's actually operating system dependent. Different operating systems have different data structures and different platforms for how they for the PCB and TCB, what they mean and so on, and different models for threading basically. But in general, or in theory, the PCB has more information about the process's address space, context switching from one process to another between a process and the kernel. Basically, is the way that you do this management of processes basically. Kernels the stuff that is ready to run now contains a mix of PCBs for processes and TCPs for kernel threads. This is again another thing that I just told you about, that now scheduling became much more complicated because you don't just schedule a process, you also schedule a thread. And you have and you might schedule a process that decides to schedule its own threads. So I mean, the scheduling is just becoming much harder now. So let us talk about the thread's life. When a thread gets suspended and evicted from the processor, because, well, the scheduler has decided that it should move on, registers such as the instruction pointer are saved, because the thread will have its own instruction pointer, because it needs to store where it is running. Implementation is operating system specific again. You either have it as part of the stack or have a separate space in the TCB for these registers. So I was talking that the thread control block has a stack and has saved registers area. The saved registers area can actually be part of the threads stack. And you have per thread metadata like the thread ID, if it's blocked by other input or ready to run, and such things. You have shared state, for example, the program code across multiple threads, because the threads are supposed to be exactly the same code. You're not supposed to have, threads are not supposed to be exactly the same code, but threads in general might share code. And let me just be more specific. But also you have statistically allocated global variables that come from basically the process. And then there are questions on what space is a normal thread running in. This is the user space. Can it corrupt the data of another thread? It should not. So these are all things that are implemented in a thread. A thread has life cycle starts from basically being created, ready to run, running, waiting for I/O. The event occurs, you're ready again, and you keep basically bouncing between the different states until you exit or you're killed, and then the thread finishes. There is something that is called the kernel threads, and these are basically threads that run inside the kernel. One of these threads that will be implemented in all Linux kernels and in all Linux machines is called the idle thread, and this is basically when there is nothing to do. You have basically absolutely nothing to run now. Your computer is an electronic device. It's not. So unless I go very deeply into how the architecture is, I'm not sure if you will get what I'm going to say next, but people who have studied architecture might know a bit about this. A processor is basically an electronic device with electronic gates, basically PNP and MP junctions and basically small electronic parts that require consistently to have electricity. The processor basically needs voltage and clock to be up for the processor to run. Otherwise, the processor just will not. I mean, everything will just die. Your computer will die. So the way that a processor is kept running is to have an idle thread, basically a thread that does nothing. And there's one thread per processor. So if you have a multi-processor machine, then you have as many idle threads as you have CPUs, and each CPU basically each processor runs a single idle thread, and the idle thread is basically responsible for making sure that the actual processor continues running. It's not like not running means that I don't give it electricity. No, you have to give it electricity for the electronic devices to run, for the transistors to continue functioning. You have to have the gates always operated with some voltage. The idle thread puts the processor in a low power sleep mode when it runs. You can actually measure the power consumption of an idle computer, and it depending on the processor architecture and on the computer. This range varies between a few watts for a small processor to 130 or 140 watts for a server to just be running idle, not doing anything. And the idle thread is the lowest priority thread. So the idle thread cannot evict any other threads, basically. It's the absolute lowest priority thing on earth. Nothing can be as low as the idle thread when it comes to priority. So as this is the lowest priority thread, it only runs when there is absolutely nothing else to run in the system. Now, as I said, there are many kernel threads, and kernel threads are basically an abstraction, a thread abstraction only available to the kernel. Again, very operating system specific, and this is exactly tied to the threading models that we were talking about. To the kernel, a kernel thread and a single-threaded user process looks quite similar. So, I mean, this distinction is rather there for the kernel to be able to handle user-level threading, rather than that the kernel itself needs to run multiple threads for a process. So it's a kernel thread is almost entirely like a single-threaded user process. Multi-threaded processes use kernel threads. For example, Linux and Mac OS do that. And kernel thread operations are available via syscalls. This is basically how your threads, how your user level threads, your application level threads, your program level threads are mapped to the kernel, to actually kernel stuff. And this is basically using these kernel threads. There is something that is called user level threads. Again, this is again related to the threading models that I was talking about. User level threads are basically the threads that you start in your program, and these threads are mapped somehow to something in the kernel. This mapping is very, very specific to each operating system. So if you have a one-to-one mapping, then for each user level thread, you will have, so if we go back to this slide, a one-to-one mapping, you will have for each user level thread, a kernel level thread equivalent to it running in the kernel. If you have n-to-one user level threading, that means that an application will have multiple threads, the kernel will create only one kernel thread for it. And then the application itself will be, or the programming language itself, or the compiler itself, or whatever is running, I mean the Java virtual machine, whatever is the program that is running, it will be responsible for actually doing this mapping, which thread should now be run from the n user level threads, and that user level thread will be mapped to the kernel level thread. And then when the user level, when the application picks another thread to run, it will just basically have to change this mapping. So now it mapped thread 1 to kernel thread 1, the only kernel thread you have basically. Now it needs to map thread to the kernel level thread. M to N is basically hybrid threading approach where it's not one-to-one, but it's not n-to-one. So I mean, you can run more than one thread in parallel, not like the n-to-one, because the n-to-one user level threading is actually meaningless, because at the end you can only run the kernel level threads. The kernel needs to use the kernel level threads to actually schedule your threads. So again, this is very operating system specific. I'm not putting this to basically, I'm not putting these slides to make you guys go confused, or basically I'm not planning to try to confuse you in an exam with these details. So I mean, this is just for you to know, because I hope that by the end of this course, when you're capable of basically choosing any operating systems book, like advanced books, and just reading it on your own. This is basically why I'm mentioning these subtle differences between the operating systems. So, a multi-threaded operating system kernel looks something along these lines. You have the kernel, and you have the user level processes. And you see, for each user level process, I mean, this is basically a non-multi-threaded version. Okay, this is or a one-to-one mapping. Basically, you have a process one running a single thread, and it's mapped to process one PCB and process two thread